Every day, telescopes and satellite arrays pour billions of data points into archives around the world. Most of that information confirms what we already expect. Stars burn at predicted temperatures. Galaxies drift along paths our models anticipate. The universe, in broad strokes, behaves. But buried inside these enormous datasets, occasionally, something surfaces that should not be there. A pattern emerges from the noise, faint and persistent, defying the assumptions that guided the observation in the first place. And the unsettling part is not the pattern itself. It is the fact that no one was looking for it. To understand what this means, we need to appreciate the scale of the problem. Modern astronomical surveys do not produce tidy, human-readable charts. They generate multidimensional arrays of raw measurements, sometimes called data tensors, structures that organize observations across many axes simultaneously. An image captured by a space telescope is not simply a photograph. It is a layered assembly of intensity values, wavelength channels, timestamps, and detector coordinates. When observations span months or years, these tensors grow to contain hundreds of millions of entries, far beyond what any human analyst could sift through by hand. The sheer volume means that most of this data is never examined directly by a person. It flows into pipelines, gets processed, and either confirms existing models or gets archived without further scrutiny. This is where the challenge begins. When you are searching for something unexpected inside a dataset that vast, you face a fundamental paradox. You cannot look for what you do not know exists. Traditional analysis pipelines are designed around models. They test hypotheses. They ask specific questions. But a signal hidden in deep space data may be one that no model anticipated. A structure that only becomes visible when the data is examined without preconceptions about what it should contain. The pipeline, in other words, is optimized to find what we expect. It is not optimized to find what we have never imagined. In recent years, researchers have turned to a class of machine learning architectures known as autoencoders to address exactly this kind of problem. An autoencoder is an artificial neural network designed to learn efficient representations of unlabeled data. It works by compressing input information into a lower dimensional encoding, then attempting to reconstruct the original data from that compressed form. The critical insight is this: when an autoencoder encounters data that does not fit the patterns it has learned, the reconstruction fails in a specific, measurable way. That failure itself becomes the signal. The anomaly does not announce itself. It is revealed by the system's inability to explain it away. Think of it as training a system on everything that is normal, then asking it to reproduce a new observation. If the reproduction is poor, if the reconstruction error spikes, the system is telling you that something in this data does not match anything it has seen before. The anomaly reveals itself not through detection, but through the failure of expectation. This is a subtle but profound inversion of how science traditionally works. Instead of predicting what should be there and confirming it, you are characterizing what is ordinary and waiting for something to refuse that characterization. This method belongs to the broader field of deep learning, which utilizes multi-layered neural networks to perform tasks such as classification, regression, and representation learning. The adjective deep refers to the stacking of multiple processing layers, each transforming the data into progressively more abstract representations. These architectures can identify structures that would be invisible to traditional statistical tests, because they do not require a prior hypothesis about what that structure might look like. They learn the shape of normality from the data itself, and anything that falls outside that learned shape becomes a candidate for further investigation. But here we must be honest about the limits. A machine learning system is not an oracle. It is a pattern recognizer trained on finite data. When an autoencoder flags an anomaly, it does not tell you what caused it. It cannot distinguish between a genuine astrophysical phenomenon and an instrumental artifact, a calibration error, a cosmic ray hit on the detector, or a processing glitch introduced during data augmentation. The flag is a beginning, not a conclusion. Data augmentation itself, the technique of training models on slightly modified copies of existing data to reduce overfitting, introduces its own subtle biases. When you augment a training set, you are making implicit assumptions about what variations are permissible. Those assumptions shape what the system considers normal, and therefore what it will flag as anomalous. A system trained on augmented data might miss a genuine signal if it resembles one of the artificial variations, or it might flag a mundane variation if the augmentation strategy failed to include it. This is the critical distinction that separates genuine discovery from wishful interpretation. An anomaly in the data is not the same as a discovery in the universe. It is the beginning of a question, not an answer. The proper scientific response is not excitement or certainty. It is verification. It is the patient, methodical work of ruling out every mundane explanation before allowing yourself to consider something extraordinary. So what would a genuine hidden signal look like once flagged? It would need to survive multiple independent checks. First, it must appear in more than one observation, ruling out single-event detector noise. Second, it must persist across different instruments, eliminating hardware-specific artifacts. Third, its statistical properties must be inconsistent with known sources of systematic error. And fourth, ideally, a physical model should exist that predicts the observed characteristics. Without meeting these criteria, an anomaly remains exactly that, an anomaly, not a discovery. The current leading explanation for most anomalies found through unsupervised deep learning methods in astronomical data is prosaic. The majority turn out to be instrumental artifacts or known astrophysical phenomena viewed from unusual angles or at unusual times. A smaller fraction represent genuinely rare but understood events, such as gravitational microlensing or unusual stellar variability. The truly unexplained residual, the signals that survive every check, remains vanishingly small. But vanishingly small is not zero. And yet, that residual is precisely where the next revolution in our understanding may hide. History shows that transformative discoveries often begin as inconvenient noise in someone else's dataset. Pulsars were first flagged as interference. The cosmic microwave background was initially mistaken for pigeon droppings on an antenna. The lesson is consistent. The universe does not label its most important messages. They arrive looking like errors. The decisive future test for any candidate hidden signal is reproducibility across independent instruments and analysis pipelines. If the same anomalous structure appears in data from two different telescopes, processed by two different teams using two different methods, the probability of an artifact drops dramatically. What remains is either a previously unrecognized systematic effect common to multiple instruments, or something genuinely new about the universe. That distinction may take years to resolve for any single candidate, but the framework for resolution now exists in a way it did not a decade ago. We do not yet know which hidden signals in current deep space archives will survive that test. We cannot claim that something impossible has been proven. What we can say, with confidence, is that the tools now exist to find patterns that no human could detect, in datasets too vast for any mind to search. The signal, if it is there, no longer depends on someone knowing where to look. It depends on our willingness to let the data speak without telling it what to say. And that represents a fundamental shift in how discovery works. For centuries, finding something new in the sky required a specific prediction or extraordinary luck. Now, for the first time, we can systematically search for the unexpected. We can ask a machine to tell us what does not fit. The answer might be nothing, or it might be something that reshapes our models entirely. We will not know until we look, and the looking has already begun. The universe has always hidden its deepest truths inside the noise. The difference now is that we are finally learning how to listen,